Section 2.8, linear inequalities in two variables. So a linear inequality in two variables means that instead of using an equal sign, we're simply going to be using a greater than or equal to, or greater than or equal to. But we're going to be solving them basically in the same way. Again, the only difference is that when you're multiplying or dividing by a negative number, you need to make sure that you remember to flip the inequality. A solution to a linear inequality is going to be any ordered pair that makes the inequality true. The graph of a linear inequality is going to be the set of all ordered pairs in a coordinate plane that represents the solutions. And we're going to be doing this by graphing the line of the linear inequality, and that line is going to be the boundary line. The boundary line is the line that divides the plane into two half planes. The half that we're going to shade contains the solutions, and the other half does not contain the solutions. And in the same way that when you graphed on a number line, you used a solid circle or a closed circle, we're going to be using a dashed line or a solid line. So again, if it's strictly less than or strictly greater than, we're going to be using an open or dashed line. If it's greater than or equal to or less than or equal to, we're going to be using a solid line. So before we start graphing them, we need to determine which ordered pairs are a solution to a given inequality. And we're doing this because this is the same idea that you would use when you determine a test point, so you can figure out where to shade your inequality. So for the first example, 0, -3, we're simply going to take that x-coordinate and the y-coordinate and plug them in for the x and the y. So 5 times 0 minus 2 times -3, we need to determine if that is in fact less than or equal to 6. So we have 0 plus 6. Is that less than or equal to 6? Well, 6 isn't less than, but this inequality is less than or equal to. So since 6 is less than or equal to 6, this is a solution. The second solution, the same idea. We're going to plug the 5 in for the x and the 5 in for the y, and we need to determine if this is less than or equal to 6. So we've got 25 minus 10. 15 is not less than or equal to 6, so this is not a solution. Two more examples like this. Why don't you go ahead and determine if 1, 2 is a solution and if 3, 3 is a solution, and come back and see if you get the same answers. For example C, we end up with y is less than or equal to 6, and since this is true, 1, 2 is a solution. And now go ahead and try 3, 3. And in this last example, we get 9 is less than or equal to 6, and we know that that's not true, so that is not a solution. So now let's go ahead and graph the line x is less than 5. So the first thing we need to do is graph the line x equals 5. And if you recall that x equals 5 is a vertical line, so the first thing we're going to do is draw a vertical line. And we're going to draw a vertical dashed line because it's not less than or equal to, it's simply less than. And so then we would typically pick a test point. 0, 0 is the easiest test point to pick. If we plug 0 in for x and 0 in for y, well, there's no y, but we get 0 is less than 5, so we realize that we would shade on the left or less than side of this line. Make sure you're shading the whole half plane on your graph paper. The next example, 3x minus 6y is greater than 12. So the first thing that might make this easier to graph is if we solve this for y. So when we solve this for y, subtracting the 3x from both sides, we get negative 6y is greater than or equal to negative 3x plus 12. And then we're dividing by negative 6. So again, don't forget that when we divide by a negative, we flip the inequality. So instead of being greater than, it becomes less than. Negative 3 divided by negative 6 is 1/2 x. 12 divided by negative 6 is minus 2. So we need to graph the line y equals 1/2 x minus 2. Starting at the y-intercept of negative 2, and then our slope is rise 1, run 2. So we're going to graph a number of these points to correctly graph our slope. And it's less than or equal to, so it's going to be a solid line that we're going to graph. And then again, we need to pick a test point. So if we pick the test point of 0, 0, and if we were to go ahead and plug 0, 0 into our equation, 0 is less than 1/2 times 0 minus 2, we get 0 is less than negative 2. 0 is not less than negative 2, so that tells us that this side makes it false. This side would be true, and so we're going to shade on the side that makes the inequality true. The next example, you have two summer jobs. One pays $9 an hour and the other pays $12 an hour. You would like to earn at least $240 a week. Write an inequality describing the possible amounts of time you can schedule at both jobs. Graph the inequality. So when we're writing an equation, the first thing we need to do is define what our x represents and what our y represents. We have two jobs, so our x is going to be the hours that we're going to earn at our job 1, and y can be our hours that we're going to work at job 2. And so we're going to fall into the familiar model of price per hour times the number of hours is the amount of money I'm going to earn at job 1, plus price per hour times the number of hours is what I'm going to earn at job 2, and this is going to end up telling me the total amount of money I'm going to make. So this is the general form of the equation that I'm going to write. So $9 an hour times the number of hours plus $12 an hour times the number of hours is going to give us $240. But now we want to make at least $240, so we need to be able to put an inequality in here. So let's think about this for a second. 9x plus 12y is the amount of money that I'm actually going to make. 240 is what I would like to make. So we can make more than we would like to make, so we're going to put a greater than or equal sign in there. And now we're going to go ahead and solve this. So go ahead and pause the video and solve this equation for y so that we can easily graph it. So when we solve the equation, we get y is greater than or equal to negative 3/4 x plus 20. And now we need to try to graph that. So two things I want to point out about graphing this. First of all, I made my scale go by 20, so I could easily get the y-intercept of 20 on there. So my scale goes by 2's, I'm sorry. And second of all, if you notice, I only drew the first quadrant, because when we're dealing with a real-life example, my x and my y axes represent the number of hours, and I can't work a negative number of hours. So typically with a real-life problem, you're going to be limiting yourself to the first quadrant. And so second of all, if I have my y-intercept of 20, as long as the scale on my x and y axis are the same, then I can count boxes for my slope, because if I'm actually going down 3, if my scale is 2, I'm going down 6 and over 8. But that's still going to be a slope of negative 3/4. So again, down 3 over 4. And I could see that my line is going to look something like that. Again, if I pick a test point of 0, 0, we can see by plugging it into the original equation, 0 plus 0 greater than 240, so this is false, and I'm going to be shading anywhere on the right or upper side of my line. And so now to identify three possible solutions, when I'm identifying three possible solutions, I can basically pick any ordered pair that's in this shaded region, and that would be the number of hours that I could schedule at my two jobs. You need to be careful because obviously there's a limit to the top number of hours that you could work at both jobs. There's a limited number of hours at work, but we would be reasonable probably and be picking numbers relatively close to that line. And the final example, graphing a absolute value linear inequality. So again, the first thing we need to do is be able to graph this absolute value. So as we were doing before, we need to identify the vertex is -2, -1, and our a value or slope is -1, so it's going to open down. So now go ahead and graph this on your note packet. So it opens down. I graphed my vertex and my slope of -1, and you need to remember that this is strictly less than, so it's going to be a dashed line with my absolute value. And again, we need to pick a test point. So now let's go ahead and try that test point. If I plug in 0 is less than -0 plus 2 minus 1, well, 0 plus 2 is 2, and the absolute value of that is 2, but I still have that negative that's in front of the absolute value, so -2 minus 1. So I get 0 is less than -3. And this test point is false because 0 is not less than -3. With absolute value, when you're shading for an absolute value inequality, you're either going to be shading everywhere outside the V, or in this case, you're going to be shading inside the V, so just inside the V. And that would be the solution to this absolute value linear inequality. If you have any questions, please make sure you bring them to class. And as another reminder, please make sure you're remembering to go back and do the notes check. And we'll see you in class tomorrow. This is the last section of this chapter, so you should maybe look over your note packet, and if you have any questions on anything from the chapter, this would be a fantastic time to ask those questions.